This will be the discussion for Lab 2526, the Respiratory Physiology Laboratory. I think this is probably one of the more difficult laboratories we have for the students for a number of reasons. One is the short turnaround time typically between the two lab exams. The other factor is that generally this lab is completed well before we've had an opportunity to discuss the respiratory physiology in the lecture portion of the class. So that makes it difficult as well. And I also think it's difficult just because of the nature of the material. So all that adds up to one of the more difficult labs we have this semester. So pay close attention to it. So one of the things that we did for laboratory is we looked at the vital capacity measurements on a spirometer. Remember, the spirometer is designed for you to only exhale in. If you wanted to inhale and exhale on the machine, you would need a respirometer. The respirometer also would have to be disinfected between each use, which again, for our laboratory purposes, is very, very difficult to do. So some people try to measure other respiratory variables on a spirometer. It just really doesn't work very well. And basically, I think they work best for just measuring a respiratory variable called vital capacity. Vital capacity is a maximum breath in and then followed by a maximum breath out. And we're measuring the volume of that maximum breath out. And to do that, we just exhale into the spirometry. The spirometer, we have the handheld ones that you saw in the other video, or there's the water one, the wet spirometer. There's a few other types too as well. So let's say we measure the capacity, their vital capacity, which we call VC, which is another thing that sort of complicates this. Is I think sometimes students get a little bent out of shape about the different terminology we have, and the terminology is often abbreviations, and the respiratory symbols become sort of difficult as well. It's another place where students tend to struggle a little bit. So the vital capacity is known as VC, and so you take a spirometer, you hold on to it, you put your mouthpiece on, you plug your nose or put a nose clip on is probably the best scientific way to do it. Take a maximum breath in, holding the spirometer off to the side, and then maximally blow through it and measure what the volume of air you could blow through it. Once you do that, though, what does that mean? And so one of the things that helps is using the age and height in centimeters to predict what your vital capacity would be from a table. There's one in Fox, and I've also, we'll see in a second, provided one from the internet. It's not Fox's one. It's very similar, though, and really you kind of see the same things. To get the height in centimeters, right, most people know their height in feet and inches, right? So you figure out how many inches it is, and then multiply by 2.54, and that'll give you your centimeters. And then once we have that, we can determine what's called the percent predicted. And the percent predicted uses the following equation. The percent predicted equals the measured vital capacity. So the measured one is what we got off that machine, divided by the predicted vital capacity. That's what you get from reading the table. And then to get the percent part, you times by 100. So as an example, if we had somebody who was 21-year-old female, 21-year-old female, it says here. So one of the things you see in Fox is he has a table for the females and a different table for the males. And body size obviously makes a difference. The larger you are, the bigger vital capacity we'd expect. But also gender makes a difference. So males tend to have higher vital capacities than females of similar age and height. So we have this female. So this is the female table that I pulled off the internet. She's 21-year-old, which is going to be an issue for us in a second. And she's 5'3" tall. All right. So couple things that we have to, note on the thing, on this table. First of all, there's an age column, right? And notice the age column falls, for the most part, after age 17, every 2 years. So there is no 21-year-old female on the table. We'll talk about what we have to do for that. But we also have someone who is 5'3". So 5 feet, right? 12 inches in a foot. So that's 60. And then 3 more inches, that's 63. So to figure out what the centimeters are for this person, we just take 63 inches multiplied by 2.54. We get 160 centimeters. So I cut this table off right at 160 centimeters to make it easy to find, right? And I didn't cut off the top because I wanted to make sure we had the identification for the rows and columns. So we got 160 centimeters. So we're going to be in this 60 centimeter column, right? And we've got age 21, I mean. And so I need to change this. We move to the 22 and 20 row. So I have it here, right? So since 21 is between the age 20 and 22, we come to this and we say, okay, they're somewhere between 3170 and 3135. So since we have those two numbers, and the person obviously is halfway in between with age 21, we just basically interpolate between the numbers. So the easiest way to do is just take, okay, there's 35 mLs difference. These values are in milliliters. So since we're going to be halfway, because we're halfway with the age, we take 35 divided by 2, which is 17-ish. And then I find it easier to add 3135 plus 17. So it's about 3152. So we're going to get 3152 in terms of our predicted vital capacity, right? And again, that's right between these two numbers, and you just basically take your best guesstimate. Scientifically, we say interpolate. So once we know that, let's determine the percent predicted for our subject using the equation we saw previously. And let's say that their vital capacity measured was 2950, so 2,950 mLs that they blew on the spirometer. So for the percent predicted, we take what they did, 2950, that's what they blew, divided by 3152. Again, that was the interpolated value off 21-year age and 160 centimeters high, right? And then times 100, so their percent predicted would be 93.6%. Normal vital capacity is generally considered to be any value over 70% are predicted. So from a medical standpoint, we really don't typically worry about people and their vital capacity as long as it's over 70% are predicted. So this subject, even though they're less than 100, still has a totally normal response. Okay, so that's not too difficult in terms of figuring out the vital capacity and percent predicted. We also looked at lesson 8 in the BioPack. And for lesson 8 in the BioPack, we did a couple things. And one of the things I added, and I'm going to go way up here, was the chest strap picture and the thermistor picture. Some people actually call it a thermistor without even the R, which doesn't make any sense to me, but you see it sometimes. So the idea was that you put this chest strap on that is pretty tight, and it's hard to see, but right there's a little knob that goes completely through. So it's like a plastic screw. And when the elastic straps go around the chest and the person inhales and exhales, that stretches the elastic as it stretches the chest itself. And that pulls on that little plastic screw, and that sends an electrical signal that's picked up by the BioPack machine and analyzed by the computer. This is the rapidly changing temperature probe. So again, down here it's called the thermistor. And basically, it's hard to see, but that's the end right there. And you put that right in front of the nostril, and we can very quickly and easily and accurately measure the change in temperature. So when someone breathes in, typically, and especially in a laboratory setting, the air is going to be colder than the air coming out of the body. And so we're going to measure that temperature difference. What are those temperature changes? And usually, literally, you just tape this to the face, and it seems to work the best way to do it. So when you get the person all set up, the person will have it. You can see a little piece of tape here, taped to the face with the little end right in front of the nostril. And then this is the same type of machine. It's a different model. This is a rubber chest strap. The other one was plastic. But the same idea is as this rubber stretches when they inhale, that sends a signal to the BioPak machine. So for our recording, we're recording temperature on the top channel. So that's this kind of sawtooth pattern. And interestingly enough, chest movement looks somewhat similar. Okay. So for the chest movement, which is the bottom one, right? The peak of the chest movement is when the chest expands. So we'll talk about that in a second and why we do that. And then the valley is when the chest compresses. So this is expansion, this is compression. Expansion up, compression down. It's like riding a roller coaster. So that's chest movement, and that's dictated by something called Boyle's Law. We'll get to that in a second. And then the top one is the air temperature. It's really the change in temperature. And the valleys, when we're going down, is when we're breathing room air. And the peaks are when we're blowing out warmed air. So every time we breathe in a laboratory setting, that laboratory is going to be typically 68, 72 degrees, somewhere in there. And so our body is, almost 100 degrees Fahrenheit. So that difference warms up the air. Now, obviously, if you were in a different environment, if for some reason you're in an environment that was 120 degrees and we were doing this, then it would actually be the opposite in terms of the temperature change. But in lab, it looks exactly like that. Okay. So let's talk a little about chest movement. When we move the chest, okay, what we're actually doing physiologically is we're applying something called Boyle's Law. And Boyle's Law tells us that pressure, this little half infinity sign means means proportional, right? So this is proportional, not equal technically, but proportional to 1 over volume. Okay, we'll get what that means in a second. But so this says pressure is inversely proportional to volume. So if pressure goes up, volume goes down. Okay, so a simpler, easier way to write it, even though it's technically not correct, is P, remember capital P we use for pressure, equals 1 over V. All right, and again, this tells us as pressure goes up, volume goes down, and vice versa. So in order to ventilation is the act of moving air between the atmosphere and your lungs. In order to do that, we have to change the pressure. And again, like we saw for the cardiovascular section for blood and other things, that fluids and gases, right, move because of a pressure difference. They move from a high pressure to low pressure. So if I want to move air into my lungs, which I do, then I need to change the pressure in my lungs. I cannot change the pressure in the atmosphere, but I can change the pressure in my lungs. And for air to move from the outside to the inside of my lungs, I need a pressure difference. I need the pressure in my lungs to be less than the atmosphere. So for inhalation, the way I do that is I increase the volume of my lungs. Okay, so this is what you're looking up top here at the figure. This is what your diaphragm looks at rest, and your external and internal intercostals help as well, especially for inhalation, your external intercostals. But here's the diaphragm, here's the size of my chest. So when I inhale, notice the diaphragm drops. We see the arrow going down, and the intercostal muscles, those external ones, contract and pull the chest forward and out at the same time. So by effectively increasing the volume of your thoracic cavity by dropping the diaphragm when it contracts and widening the chest walls when the external intercostals contract, and then moving the actual chest wall forward as well, that has increased the volume. Because of Boyle's law, since the volume went up, it's inversely proportional, the pressure goes down. And so now the atmospheric pressure in your lungs is less, well, sorry, I guess it's not atmospheric pressure. I guess the pressure in your lungs is less than the atmospheric pressure. And you can see the little arrows here. That moves gas into your lungs, especially oxygen. We haven't talked about it yet in lecture, but oxygen, about 21% of room air almost, and nitrogen is pretty much almost everything that's left. There's a very small percentage of gases that aren't nitrogen and oxygen in terms of what we breathe on Earth. So that's inhalation, and inhalation is dictated by Boyle's law. Well, once I get the gas in, I have to get it out, and for getting it out, I just do the opposite. So notice during exhalation, the elastic recoil, that's the diaphragm, which snaps back into place. Your external intercostal snap back into place. And we go from this large, look at the dotted line, large volume to the smaller volume. Once we've done that, remember, pressure and volume are inversely proportional. So if I have a smaller volume, I have a greater pressure, and that greater pressure is greater than the atmospheric pressure, and air moves out. Those changes in pressure are typically only a couple millimeters of mercury, 3 or 4 millimeters of mercury. So it's not a huge pressure difference, but it does have an effect in terms of getting air in and out of our lungs. And if you couldn't get a pressure difference, then you wouldn't be able to move air in and out of your lungs, and you would suffocate. So that's Boyle's law. Pressure and volume are inversely proportional. Now, when we look at the data, here's an example of the data. Remember, the bottom one is the chest movement. Okay, so notice there's chest movement here is identified. And if we want to move the chest, okay, so what we have in black, highlighted in black, is this downward chest movement. Okay, so if you look at that chest movement that's going down, we're getting a smaller chest. And so as we get a smaller chest, okay, smaller chest increases pressure, and now air starts to move out of our lungs because of this. And as air moves out of our lungs, we see the temperature go up. Why does the temperature go up? Because we've had air in our lungs previously that's a warmer temperature than the room air, so that air not only has been humidified, but it's also been warmed up. So when we exhale, the temperature goes up as well. Okay, so that's part of what we're looking at, really one of the major points of the whole thing. So we change volume first, and that moves the air, and the airflow lags behind chest movement, and the temperature then lags behind chest movement as well, because the temperature change is due to the change in airflow. So sort of like we saw for the QRS and pulse pressure wave, right? It's the volume changes in your lung that lead to the movement of gases and the change in temperature. One of the other things we were supposed to do in lesson 8, and this kind of shows it okay. I'm going to go to the next one, probably shows a little better. You're supposed to, breathe for a couple minutes normal, and then do hyperventilation. Now they ask for, 20, 30 seconds. It seems really excessive, and you could actually pass out if you hyperventilate that much. So I think you can get the data. It doesn't look much different here and here, right? So it doesn't really look different. So you could have easily, been able to measure that in 10 seconds or less. Then you kind of rest for a while. That's recovery. Then they're supposed to do hypoventilation, and then recovery. And then the last part is to read aloud. The read aloud doesn't really work very well, and you just see weird things sort of like this, which are related to your ability to read out loud, to be honest. And it really depends on what you're reading. If you're reading your textbook, it would be very different pattern than if you were reading Dr. Seuss or a children's book or a novel or something. So this doesn't really have much of applicability in terms of analyzing. But kind of look and just kind of look at the data. We're not going to measure it per se. We could do that with the computer program, and we'd be able to manipulate this data. So if you look here, that's 208 seconds worth of data, right? That's what 3.5 minutes, basically. So you can see the individual respiratory peaks and valleys because respiration is so much slower than heart rate. If this was an ECG, you wouldn't be able to see much except just the QRS waves. But you're breathing normally, and here's the big change in temperature, right? And then you hyperventilate. And when you start to hyperventilate, notice these get closer together. So by definition, you should be going faster breathing, right? And then notice what happens to the temperature change. It gets really small. And the temperature change gets really small. It's really simple. If you put something in the oven for 10 seconds, it's not going to warm up much. If you put something in for 10 minutes, it's going to get a lot warmer. And so because the respiration rate is so much faster, the hyperventilation does not allow the air to warm up that much because it's not very much in terms of your body, in your body. So you're exhaling it before it has a chance to warm up too much. So that's hyperventilation. It's interesting because some people hyperventilate, and notice these are very similar to the chest height. Sometimes people more pant than hyperventilate, so they tend to be very small. And some people get these very large, deep hyperventilations. It just depends on the individual and how they do it. And then the recovery looks kind of like the first one. And then this one was supposed to be in the middle, hypoventilation. And you can tell, like right here, especially in this middle part, that the respiratory waves are farther apart from each other, which means that it's a slower respiratory rate. But really, it's not as apparent as we often see in lab. We have much better results in terms of the hypoventilation. Like I said, we don't even do read aloud. The other thing you don't see with hypoventilation, surprisingly, is, we have students occasionally that hyperventilate that might go to 20 breaths per minute, 25, 30. I've had people go over 120 breaths per minute, so more than 2 a second for hyperventilation. For hypoventilation, I've had students be in the low teens and all the way down to like 2 breaths per minute. So, I had a student that literally took 30 seconds to take a breath and did that for 2 full minutes, I think it was. So it was pretty amazing. But typically in hypoventilation, when it gets farther apart, and you can kind of tell here, if you measure the distance between the bottom here right below the O, you can see it peeking through, and the top here, that's one of the bigger temperature changes, and that's because the person is breathing slower, and you've got a little bit longer in terms of holding the air in the lungs and the body, so you get a little better warming. But look at this. You can definitely see these are farther apart, but they're not appreciably farther apart, which means they're not that much slower. So that's why we don't see as big changes within the waves. So that was the one part of the lab where we looked at the different portions of lesson 8 and the spirometer. We're going to start a whole new video to look at the respiratory tracing calculations because it gets pretty complicated. So we'll quit with this one and start a new one. We'll have a discussion 2 for this one, next one.